Intelligence is the ability to make models, right? What is a model? A model is something that explains information. Information is discernible differences at your systemic interface, and the meaning of information is the relationships you discover to changes in other information. If you have a blip on your retina, the meaning of that blip is the relationship you discover to other blips on your retina at the same moment or at different moments in time. The relationships you discover is you are looking at a three-dimensional world with people that are deformed by the laws of perspective and being shown on by photons, and these people have ideas and exchange them with with you and so on, right? So you build this giant operator that predicts the data at your systemic interface. This is your model. And this model has 3 parameters in it. Parameters like sounds and colors and people and so on. They're not features of the physical universe out there, which is some kind of weird quantum graph that has the ability to produce patterns. The structure that we find in the patterns, these are these geometric functions that describe how objects move in space and what they sound like and what they look like. And a model is a set of parameters, which a parameter is a set of possible discrete values, and the relationships between the parameters. And the relationships are computational relationships which tell you if this parameter and this parameter have these values, then that parameter should have that value. So for instance, you figure out that a way to describe a face that you're looking at is you see the structure of the face, you see the nose and so on. And if you see both the nose and the face, they need to have the same pose, the same alignment in space, if they're connected, right? So your nose representation is going to send, via its computational relationship, information about its position in space to the face. And the face is going to send information about its position to the nose, and they need to agree. And if they don't, you have an inconsistency, an incoherence in your model. And our perception goes for coherence. It tries to find one operator that is completely coherent. When it does this, it's done. This is the way we optimize. So we try to find one stable pattern that explains as much as possible of what we can see and hear and so on, and smell and think. And attention is what we use to repair this. So whenever we have some local inconsistency where the nose is pointing in some other direction than the face, this calls attention to itself. And attention is a particular kind of mechanism in the brain that gets pulled to these areas, these hotspots where things are fluctuating and don't get resolved, and then tries to find a solution. And it might find out, oh, some noses are crooked. Oh, this is not a face, or it's a caricature. So you extend your models, and these extensions of the models make it possible to encapsulate this part of the operator that is currently of the sensory data in such a way that it's harmonious again, that it makes sense again, right? Once you do this, you're done, and you can put your attention on something else. This attentional learning cannot work like the layered stochastic gradient descent over neural networks, partially because our brain is not differentiable, also because it's a very inefficient algorithm. And the algorithm that our brain is using in these cases is that we store the local binding state. For instance, you play tennis. You want to get better at tennis. So what do? You cannot basically pipe a loss function through all of your brain in order to get better at tennis. It would be very inefficient. You need to touch too many neurons. What you do instead is you make a commitment. You say, I want to get better at this particular thing. I want to improve my backhand. So I will make this stroke slightly more like this, and I expect the following result. And I remember what this means. So I store this binding state that allows me to have that configuration in my brain to perform that stroke. This part of I store as an indexed memory. And conscious attention in this sense is the ability to make indexed memories that I can later recall. I also store the expected result and the triggering condition. When do I expect the result to be visible? So a few minutes or seconds later or hours later, I have feedback about whether this was a good decision. I won or lost the match. And then I recall my decision that I made early on. I recall that binding state. I reinstate part of my brain state back then and remember the situation that I was in. I compare the result that I expected with the result I got. And as a result, I can undo the decision that I made back then, this change in the model, or I can reinforce it. And this is, I think, the primary mode of learning that we use beyond just associative learning.
So this attention consciousness, the key differentiator in the process of learning then?
So consciousness means that you remember what you had attended to.
Right.
So you have this protocol of attention. And the memory of the binding state itself, the memory of being in that binding state, where you have this global oscillation that combines as many perceptual features as possible into a single function. The memory of that is phenomenal experience. The act of recalling this from the protocol, this is access consciousness. And you need to train this attentional system itself. How do you train the attentional system so it knows where you store your backend in your cognitive architecture? That is something that needs to be trained by the attentional system as well. So you have recursive access to the attentional protocol. You remember when you made this recall, when you access this protocol, what results you got from this. You don't do this all the time, only when you want to train this. And this is reflexive consciousness. That's the memory of the access.